on the next level, from left to right, if I write it down, it'll be 2, 3. Again, if I write down for the third level, first it's going to be 4, then it's going to be 5, then it's going to be 6, then it is going to be 7. So this is what a level order traversal will be. It's going to traverse in this fashion, then in this fashion, then in this fashion. So you have to print the level order traversal of any given binary tree. So in order to print the level order traversal in level wise, what we require initially is a queue data structure. Okay, so let's define a queue data structure. Now this queue will be initially having the root of the tree, that's 1. Now in order to store the traversal level wise, now is any given binary tree. So in order to print the level order traversal in level wise, what we require initially is a queue data structure. Okay, so let's define a queue data structure. Now this queue will be initially having the root of the tree, that's 1. Now in order to store the traversal level wise, we will be requiring some data structure. So let's take a vector of vector or an array list of array list for that reason. So I'm going to take a vector of vector which stores the level wise traversal level wise. Now these are the initial data structures that I'll be taking. Okay, now let's start iterating over this queue. So what's the first thing that I have? I have a node which is 1. So let's take this one out. Okay, so I've taken this one out. Now whenever you take this one out, please make sure that if on the left of this one, that's 2, if it exists, if the left exists, just take this left guy and put it into your queue data structure. Okay, now check the right side of 1. Just check the right side of 1. Does the right side exist? If it does exist, take this and put it into your queue data structure. Once you have done it for 1. Okay, once you've done it for 1, since there was only one guy of this level, right? What you will do is you will take this one, put it into a vector or a list, and you'll put it into your data structure which stores your traversals. So I put that. So this traversal is completed. Now in the next traversal, in the next iteration of the queue, what you will do is whatever are lined up in your queue, just take them. Whatever is lined up in your queue, just take them. You don't need to do anything extra. Just take them, whatever is lined up. Now off 2, check the left, that's a 4. On 2, check the right, that's a 5. So first 4, then 5, insert that into your queue data structure. Similarly do it for 3. For 3, on the left there is a 6, on the right there is a 7. So let's take 6, let's take 7 and insert into a queue data structure. Once on this iteration you have done for 2 and 3, again put it into a list or a vector and just make sure you put it into your data structure which is storing your level wise traversals. So I'll put 2 and 3 as of now. Perfect. Then the next iteration, you have these 4 elements. That's your next iteration, right? You have these 4 elements. So what you will do as of now is you'll take these guys out, 4, 5, 6, 7. So 4 is taken, 5 is taken, 6 is taken, 7 is taken. Does 4 have a left? No. Does 4 have a right? No. Does 5 have a left? No. Does 5 have a right? No. Does 6 have a left? No. So similarly, no one has a left or a right. So if it doesn't have, you don't need to push anything into the queue. Now take these 4 guys out, put it into a vector and put this into your required answer data structure, which is 4, 5, 6 and 7. So once this is done, you can say your traversal is completed, and if you carefully observe, your queue data structure is indeed empty now. Whenever this is empty, you can say this data structure stores your level order traversal. So this is how you're going to store the level order traversal. So I hope you have understood how to do a level order traversal on any given binary tree, right? Now let's quickly check out the code. So guys, I'm going to discuss the C++ as well as the Java code. So on the left side, you can see the C++ code. On the right side, you can see the Java code. So initially, you can see that you're given the root of the binary tree, right? So what we can see is, initially I've declared the data structure which is going to store the list or the level wise traversals. Right after that, I see if the tree that is given to us, if that is empty, I'm going to turn an empty data structure saying that I don't have any level wise traversals. After that, I have defined a queue data structure, right? That's the line. And I'm saying queue.push root. So this is the moment when I make sure that I have all the initial configs ready. Right after that, I just make sure that I take the size. So whatever is the number of elements, for the first time I will have 1, For the next time, I'll have 2, 3. For the next time, I will definitely have 4, 5, 6, 7, 4 elements. So I take the size of the element, and whatever is the size, I basically traverse for that. So that means I'll traverse for 2, 3. In the next time, I'll traverse for 4, 5, 6, 7. So this traversal is done using this for loop. Okay. Right after that, what I'm doing is I'm taking the node. That means I'm just taking 2, 3, or 4, 5, 6, 7. This is the first iteration. This is the second iteration. This is the third iteration. Across, I'm taking every node. So what am I doing is I'm taking that node and I'm popping it out, and whatever node I'm taking, if there exists a left, I'm pushing it into the queue. If there exists a right, I'm pushing it into the queue, right? And once it is done, I'm storing that node. Yes, I'm storing that node into some vector. So once the complete iteration is completed, I'll take this vector level and I'll put it into my answer. Got it? So this is how after the entire iteration I can say my this data structure, which is answer, will be storing the entire level wise traversal, and I can easily return it. So guys, this is how the level wise traversal will look like. And so guys, if I discuss about the time complexity, that's a big O of n, because as you saw, you traverse for 1 node, 2 node, 3 node, 4 node, 5 node, 6 node, 7 nodes. So there are 7 nodes, or big O of n. What is the space complexity? Again, I can say it's a big O of n, because at the worst case, your queue is going to store all the nodes in itself at a time. Like that can be the worst case. And will we take into account that complexity which this answer data structure is? No, we generally do not take into account that, because that is what we are returning, right? That is where we are storing and returning. So that's not taken. So in usual, I can say the time complexity of level order is big of n, and the space complexity is also big O of n. So I hope you've understood the entire explanation. So before starting off this video, I'd love to thank Reliable for sponsoring this entire tree series. We need experienced candidates. How many times has this sentence shattered your dream to work in a good company, or a job description which requires experience? You won't ever have to listen to the sentence ever again if you use a platform like Reliable by Unacademy. He conducts a test which is completely based on skills and you need to perform in your chosen field. Reliable has around 1,000 plus job openings by 50 plus top Indian companies and unicorn startups. What you need to do is you just need to register for this test, apply on the test, and after that your interview will be scheduled and you will be hired. And the best thing about this is the Reliable tests are free and you can check out all the links in the description below. Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we are going to solve the pre-order traversal, not using recursion, but iterative traversal, where I'll be using a stacked data structure. What is a pre-order traversal? Root, left, right. Now, if I try to write the pre-order traversal of this particular tree, I'll get 1 at first. Then I have to go to the left. Remember, first root, then I have to go to the left. So this is the entire left. So once I go to the left, I have to again apply root, left, right. So this will be the root. I have to again go to the left. So this will be the root now. Now this is the moment I can say that, okay, that's 1, 2, 3. So now I'll come back and I'll go to the right. When I go to the right, 4, 5, 6 is a tree. So I will have to print 4. And then it's a left, that's 5. Then it's a right of 6. So I've printed this, right? Once 1 is printed and once the entire left is printed, it's time to come back to the right, and the right has 7. So this is going to be the pre-order traversal of this particular binary tree. So how do you solve this without recursion? Very simple. What you do is you take a stack. Now you know what's a stack? A stack is a last in first out data structure. So once you have taken a stack, what you will do is whatever, yes, I repeat, whatever is at the root of the tree, just make sure you put it onto your stack. Okay, so you put that onto your stack. So this is how you'll start off with. Now let's start the traversal. At first, whatever is on the top of the stack, take it out and print. So the first node of your pre-order traversal is printed. Right after that, at first take the right and then take the left and put it into your stack. So first take the right and then take the left. That's 2. Why did I take the right and then the left? Because you know it's a left and right. So first I have to travel for 2, then for 7. That's why, since stack is a last in first out, I put in 7 and then 2. Got it? So right after this, what I'll do is, in the next traversal when I come back, I'll get the topmost element. That's 2. So I'll print it. Very simple, I printed it. Now again I'll do the same thing. So next I'll take the right guy, that's 4. And then I'll take the left guy, that's 3. So you'll simply take it. Perfect. Now in the next traversal when you come across, you will get 3. So you will print 3. Now once you've printed 3, 3's right is nothing, 3's left is nothing. So this traversal cannot find anything on the left and right. So 3 is completed. On the next traversal, you will figure out 4. So 4 is printed. Now when you have figured out 4, first you'll take 4 ka right, that is 6. Then you'll take 4 ka left, that is 5. So just take it and put it into your stack. So I can say 4 is also completed. Now in the next iteration when you come back, you have a 5. So please take 5 and print it into your pre-order. Next, does 5 have a right? No. Does 5 have a left? No. So 5 is also done. At the next iteration when you come back, you will have a 6. So take 6 and print it. So 6 is also done. Now does 6 have a right? No. Does 6 have a left? No. Nothing to be inserted. The next moment, since all things on the left of 1 is completed, when in the next iteration you'll come across 7 and you'll print out 7. The moment you print out 7, there is nothing on the right, there is nothing on the left. So in the next iteration, when you see, the stack becomes empty. The moment the stack becomes empty, I can end and I can say that the entire pre-ordered traversal was indeed printed. So guys, as usual, the C++ code is on the left and the Java code is on the right. So you're given the root of the tree. You declare a vector or a list, and if the root is null, that means the tree is empty. You return an empty pre-order, right? Right after that, what do? You take a stack, and initially you have the root, and you keep on iterating on the stack till it is non-empty. Perfect. After that, you get the topmost element. Once you get that, that is going to be your pre-order. So in every iteration, get the topmost of stack, and that's your pre-order. Once that is done, check out if there exists a right, put it. Check out if there exists a left, and put it into your stack. Once the entire stack becomes empty, return the pre-order, which is going to be answer, or with the time complexity. The time complexity is big of n because see, you're gonna travel for right almost equivalent to big of n. You'll always big of c. I can say the space complexity at the worst case is big of n. The worst case of space complexity will happen. Just imagine if you have something like this, topmost element. The next traverse is also done. Now does 6 have a on the left you see the stack. Alright, so basically return the server. Iterating on the stack, empty the Java code is on the right. So you're given the root of the tree. You declare a vector or a list, And if the root is null, that means the tree is empty. You return an empty pre-order, right? Right after that, what do? You take a stack, and initially you have the root, and you keep on iterating on the stack till it is non-empty. Perfect. After that, you get the topmost element. So once you get that, that is going to be your pre-order. So in every iteration, get the topmost of stack, and that's your pre-order. Once that is done, check out if there exists a right, put it. Check out if there exists a left, and put it into your stack. Once the entire stack becomes empty, return the pre-order, which is going to be answer. What is the time complexity? The time complexity is big of n, because see, you're going to travel for every node, right? You're going to travel for every node. So that's a big of n. What about the space complexity? I can say the space complexity at the worst case is big of n. The worst case of space complexity will happen. Just imagine if you have something like this. A right, a right, a right. So basically, you'll always keep on having right, left. So the stack space, like the stack space will be a lot if you consider a tree which is only having like one right node always. So the stack space will be almost equivalent to big of n, or I can generalize it to write as big of height of the binary tree will be So before starting this video, I'd love to thank Reliable for sponsoring this entire tree series. Did you know that tells you that you cannot use recursion? Then how will you solve this problem? We're going to use an go to the left. 4 is the first node. Then you go to its root, that's 2. Then you go to the right. So this is the right subtree. And this right subtree again left, root, right. So 6, 5, 7. So the left portion is completed. So you come back to root, that's 1. Then you go to the right, that's 3. That is how you generally do left, root, right. So this is going to be the in order traversal of this particular binary tree. So you know recursive way, right? So if you remember, in the recursion, what we did was we moved to the left, we printed, and then we moved to right. So basically what happened was we went to the left, again we came to the left, again we came to the left, and the moment the left was complete, then we printed that node. Basically I went to 1, then I went to 2, then I went to 4, and then I printed 4. And this one, like at first the call was made for 1, it went to the left, then 2, then it went to 4, and at the end the 4 was printed. So these 2 and 1 were stored in the auxiliary stack space of recursion, right? Auxiliary stack space of recursion. Over here, in order to convert this into an iterative solution, can I not use a stack which is created by me? Yes, I can. And I store the similar thing like 1, 2, and I can just reuse them. I think that makes absolute sense. So let's do that. So in order to have an iterative traversal, just make sure you have a stack data structure. Okay. So what's a stack data structure? It's a last in, first out data structure. That is what you will have. And also have a node which is initialized to the root initially. So currently you are at the node 1. Let's start the iteration. Now remember, at every step of iteration, you take whatever is at the node. Remember this. If this is not null, you take this and you put it into your stack. Okay. Once you have put it into your stack, if there exists a left, like even if there doesn't, you just take the left of 1. So you'll take the left of 1. So in every iteration, if the node is not null, you'll take this and you'll put it into your stack and you'll move to the left. Similar to recursion where you move to the left. Now, in the next iteration, you come to 2 again. Same thing, take it and put it into your stack. And now it's time to move to the left. Similar to recursion, I'll move to the left. And the next iteration, you come back again and you have a 4. Again, just store it and move to the next. So move to the left. So when you move to the left, you will get null. So in the next iteration, when you come, you see that there is a null. Remember, if there is a null, there is no need to move to the left any further. So similar to recursion, what you will do is you will just take out this element and you'll print it. So the first element 4 is indeed printed. That is the in order traversal. Right after that, you know you have to move to the right. If you remember recursion, left, print, right. So you have to move to the right. So who is force right? Do you have anything? No. So this guy again gets converted to null because force right is null, and that is what you will make the node as. Iteration over. Again come back to the next iteration. Now when you come back to the next iteration, you again have a null. If you again have a null, it's the same thing. Come back. So you'll take this 2 and you'll print it. So you're coming back, right? If it's a null, if you remember the recursion code, if it's a null, you have to come back, right? So I've came back. You have printed 2, right? Now since you have taken 2 and printed, if you remember it was left, root, right. So it's time to move to 2's right. What's 2's right? 5. So this is what I will do. I'll take out the top of the stack, I'll print it, and now it's time to move to the right. So I'll move to the right. Perfect. In the next iteration, when I come across, I will take this 5 and I'll put this into the stack. I'll assign that. So 5 right now left of 7. So I'll move to null. Now, and that's time. Just take it. If it's level or the travel, getting through the else. What does plus code is on the same stack trace being created. So as usual, the C++ code is on the left and the Java code is on the right. So what are we given? We are given the root of the tree, right? And we take a stack, empty stack. I create a node which is our current or whatever you can call. I can just assign it to root, and I've declared a vector which stores my in order. Now if you remember what we did, if the node is not null, we took that node, we put that into the stack, and we moved to the left. Basically this creates my stack auxiliary stack trace, and I move to the left. Perfect. And at the same iteration, if I end up getting through the else, what does else means? It means it's null, right? If it is null, if you remember, what did we do? We will just make sure if the stack is empty, then it's over. That means there are no nodes to travel, or else whatever is at the top of the stack, we take it, okay? And that will be my in order. And after that, since it is print, and after that it's right, I move to the right, and the iteration goes over. Whenever the stack becomes empty, I'll break out. Once I break out, I'm going to return the in order traversal. What will be the time complexity, guys? It's very simple. It's right. So who is force right? Do you have anything? No. So this guy again gets converted to null because force right is null, and that is what you will make the node as. Iteration over. Again come back to the next iteration. Now when you come back to the next iteration, you again have a null. If you again have a null, it's the same thing. Come back. So you'll take this 2 and you'll print it. So you're coming back, right? If it's a null, if you remember the recursion code, if it's a null, you have to come back, right? So I've came back. You have printed 2, right? Now since you have taken 2 and printed, if you remember, it was left, root, right. So it's time to move to 2's right. What's 2's right? 5. So this is what I will do. I'll take out the top of the stack, I'll print it, and now it's time to move to the right. So I'll move to the right. Perfect. In the next iteration, when I come across, I will take this 5 and I'll put this into the stack, okay? And at the same time, I will move to the left of 5 because this 5 will wait, and I'll move to the left. That is 6. Let's move to the 6. Then the next iteration, when I come back again I'll take this 6 and I'll make it wait, and I'll move to the left. So when I move to the left, it's a null again. Perfect. If it's a null again, in the next iteration, what will happen? It will say I'm a null. So I will take the top of the stack. And what is the top of the stack? 6. So I'll print this 6. And what I will do is left print right. So 6 is right is null again. So I'll just reassign that to null. So I've reassigned that to null. Perfect. In the next iteration, when I come across, I again get a null. So what I will do is I will take back the last guy, 5, and I'll print it. Once I've printed it, you're getting a pattern, right? First it was 6, then it was 5, so it is coming back, it is backtracking. First 6, then 5, it is backtracking. So since you have printed 5, so left root is printed, time to go to the right. So 5's right is 7. So this guy will change to 7. So I'll come to the right now, I'll come to 7. Perfect. And the next iteration, when I come back, I see I have a 7. So I'll take that and put into the stack, and I will move to the left of 7. So I'll move to null. And the next iteration, when I come back, I see a null. If it's a null, what I'll do is I'll take this 7 and I'll print it. And since it is printed, now it's time to move to the right. 7's right is null. So I'll move to null. Perfect. Now the next iteration, when I come across, I again see a null. Now this moment, when I see a null, what happens? Very simple. I take the topmost element again, and that is what is printed. Once that is printed, I will reassign this to the right of 1 because 1 is printed. It's time to go to the right of 1. Left print right. So the right of 1 is nothing but 3. So I went to 3. And the next iteration, when I come back, I have a 3. So I go to the left of 3. Yes, in the next iteration, when I come back, I have a 3. So just take it and put it into your stack. And now it's time that you change this to the left. So the left is null. In the next iteration, when you come back, you see there is a null. So whatever is over here, you just take it out and you print and you move to the right of 3. That's null.
everything changes. You won't reply, I'ma go back to strangers. It's something that I hate, how everyone's disposable. Every time I date somebody new, I feel vulnerable, that it'll never change, and it'll just stay like this. Never ending dating, breaking up, and it goes like this. We'll get in your car and you'll need to kiss me. We'll talk for hours and lie on the backseat. And then one random night when everything changes, you won't reply, I'ma go back to strangers. It always ends the same when it was me and you. But every time I meet somebody new, it's like deja vu. And when we spoke for months, what did you ever mean? And how can they say that this is love when it goes like this? We'll get in your car and you'll need to kiss me. We'll talk for hours and lie on the backseat. And then one random night when everything changes, you won't reply, I'ma go back to strangers.
post order traversal, not using recursion, rather. Now what you will do initially is you'll take the root of the tree and you'll enter that into the stack one. That's the initial configuration. That is what your initial configuration will be when you start off with. Now let's get started. So when you start the program, you take the first guy out. And the moment you take this out, you put that into your stack. Okay. After that, if this guy has a left that it has, you'll take that. If this guy has a right, you'll take that. So you have taken the left as well as right. Now at the next step, at the next iteration when you come across stack dot top, the top element is 3. So take this 3, put this into your stack. Okay. And again, same thing. Stacks left, that is 6. Stacks right, that is empty. So if it is empty, you don't need to put, but put the left. So I put it right. Now again, come back on the next iteration. Take whatever is at the top, put it onto your stack. Okay. So I put that into your other stack. Next, what do we have? Before starting this video, I'll love stack trace or stack space. So I've already discussed the intuition. You try to go to left, 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 and then a right, and then again left, 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 then a right, then again left, left, left. And I know the post order is left, right, root. So next, what we have taken, if there is a left of 6, take it. If there's a right of 6, take it and put it into your stack. Perfect. Now what is in the next iteration? When you come across, you get 7. So you'll take 7, you'll put that into your stack 2. Once you put that into your stack 2, for 7, does there exist a left? No. Does there exist a right? Yes. Take it and put that into your stack. In the next iteration when you come across, take this 8, put that into your stack 2. And again, does 8 have a left? No. Does 8 have a right? No. So you'll not do anything. In the next iteration when you come back, you'll get a 2. So take this 2 and put that into your stack 2. Now what you'll do is, you'll again look, does the 2 have a left? Yes. Does the 2 have a right? Yes. Put them in. Next, you'll again come back, stack dot top, take it and put it into your stack 2. Does 5 have a left? No. Does 5 have a right? No. Next, again come back, you get a 4. Does 4 have a left? No. Does 4 have a right? No. So this will be, the 4 will be the last one. So once your stack 1 becomes empty, you can stop. And the moment you stop, take these elements out from the stack in the last in first out fashion. So first 4 will be up, so you'll get 4. Then 5 will be up, so you'll get 5. Then 2 will be up, so you'll get 2. Then 8 will be up, so you'll get 8. Then 7 will be up, so you'll get 7. Then 6 will be up, so you'll get 6. Then 3 will be up, so you'll get 3. Then 1 will be up, so you'll get 1. Academy is here to make your dream come simple. Will be apply for video. I'll solve this using a single stack. So what is a post order traversal? It's nothing but left first. Go to the right. That's 5. Then I will go to the root. That's 2. So this tree is done. Now on this tree, the left is done. So I'll have to go to the right. So right I'll go. Now if I'm on the right, I have to go to the left. Right. Then I have to go to the right. Then on this I have to go to the right. So it's going to be 8. Then a 7. Then a 6. Then a 3. Then a 1. That is what the post order traversal for this given binary tree will be. So what we will do is we will initially take 2 stacks. This is the first stack, stack 1 that I take. Then I'll be taking stack 2. Okay, so let's take stack 2. Now what you will do initially is you'll take the root of the tree and you'll enter that into the stack 1. That's the initial configuration. That is what your initial configuration will be when you start off with. Now let's get started. So when you start the program, you take the first guy out. And the moment you take this out, you put that into your stack. Okay. After that, if this guy has a left that it has, you'll take that. If this guy has a right, you'll take that. So you have taken the left as well as right. Now at the next step, at the next iteration when you come across stack dot top, the top element is 3. So take this 3, put this into your stack. Okay. And again, same thing. Stacks left, that is 6. Stacks right, that is empty. So if it is empty, you don't need to put, but put the left. Your stack. Okay. And again, same thing. Stacks left, that is 6. Stacks right, that is empty. So if it is empty, you don't need to put, but put the left. So I put it right. Now again, come back on the next iteration. Take whatever is at the top, put it onto your stack. Okay, so I put that into your other stack. Next, what we have taken, if there is a left of 6, take it. If there's a right of 6, take it and put it into your stack. Perfect. Now what is in the next iteration? When you come across, you get 7. So you'll take 7, you'll put that into your stack 2. Once you put that into your stack 2, for 7, does there exist a left? No. Does there exist a right? Yes. Take it and put that into your stack. In the next iteration when you come across, take this 8, put that into your stack 2. And again, does 8 have a left? No. Does 8 have a right? No. So you'll not do anything. In the next iteration when you come back, you'll get a 2. So take this 2 and put that into your stack 2. Now what you'll do is, you'll again look, does the 2 have a left? Yes. Does the 2 have a right? Yes. Put them in. Next, you'll again come back, stack dot top, take it and put it into your stack 2. Does 5 have a left? No. Does 5 have a right? No. Next, again come back, you get a 4. Does 4 have a left? No. Does 4 have a right? No. So this will be, the 4 will be the last one. So once your stack 1 becomes empty, you can stop. And the moment you stop, take these elements out from the stack in the last in first out fashion. So first 4 will be up, so you'll get 4. Then 5 will be up, so you'll get 5. Then 2 will be up, so you'll get 2. Then 8 will be up, so you'll get 8. Then 7 will be up, so you'll get 7. Then 6 will be up, so you'll get 6. Then 3 will be up, so you'll get 3. Then 1 will be up, so you'll get 1. So ultimately, you will get the entire post order traversal using a couple of stacks. So let's check out the code for this. So as usual, you know the C++ code is on the left and the Java code is definitely on the right. So initially what I've done is I've taken the root and I've defined a post order list of vector. And if it is null, if the binary tree is null, I'll return an empty post order. Or else I'll declare a stack and I'll be entering the root on the left and the Java code is definitely on the couple of stacks. So let's check out the code for this. So as usual, you know the C++ code is on the left and the Java code is definitely on the right. So initially what I've done is I've taken the root and I've defined a post order list of vector. And if it is null, if the binary tree is null, I'll return an empty post order. Or else I'll declare a stack and I'll be entering the root initially into the stack. So what I've done is I've taken the topmost element and I've pushed it into the other stack. After that, if there exists a left, put it onto the stack 1. If there exists a right, put it onto your stack 1. Once your stack 1 becomes empty, just pop out every element from stack 2 and put it into your post order and return that post order. So what is the time complexity of the solution? Definitely we go often because you are ultimately a list of vector, and if it is null, if the binary tree is null, I'll return an empty post order, or else I'll declare a stack and I'll be entering the root initially into the stack. So what I've done is I've taken the topmost element and I've pushed it into the other stack. After that, if there exists a left, put it onto the stack 1. If there exists a right, put it onto your stack 1. Once your stack 1 becomes empty, just pop out every element from stack 2 and put it into your post order and return that post order. So what is the time complexity of this solution? Definitely we go often because you are ultimately traversing for a value and return. We do not consider that while computing, but you can still consider that if you want. And then it's 2n plus n. So the main problem that we are facing is we're using a couple of stacks. Okay. So in the next video, I'll be telling you how can we solve this next. Again, come back. This is the algorithm. Then go to the right, and then when the right again recursion call, then right it was right. Then you go to right. Traversal can be done iteratively using couple of stacks. But in this video, I'll tell you how to do this using one stack. So what's a post order traversal? It's basically nothing but left, then you go to right, and then it's the root. So it's a left, right, root. That is what a post order traversal is. So what did you do in the recursion? If you remember, it was left, then it was right, then it was print. So logically thinking, it was kind of go to left, 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 and then when it ended, then go to the right, and then when the right again recursion call, then right ka again go to left, 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 and again when the recursion ended, then go to the right, then again left, 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 then again right, and then after that you printed right. Then after that, when you came back, the right got printed. So it's kind of a go left, go left, go left, and the moment it gets you something as null, try to go right, and then again go left, 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 right. So that is how our algorithm will focus on, and we're going to use an external stack in order to maintain the stack trace or stack space. So I've already discussed the intuition. You try to go to left, 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 and then a right, and then again left, 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 then a right, then again left, left, left. And I know the post order is left, right, root. So this is the algorithm that I've already written. Why have I written it prior to this? Because otherwise it will get very tricky to understand. So I've written the algorithm. I'll do a dry run. And when I do the dry run, you will see that the intuition is being applied over here. The going of left, 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 and then right, and then left, left, left. The intuition is being applied. So let's start. So what you will start is, you will take a curve and I'll point to the root of the node. Okay, I'll point to the root of the node. Remember this. And you'll take a stack. So take a stack, and stack is nothing but a last in, first out data structure. So just take a stack which is pointing to which is empty, and start the traversal and try to go as left as possible. So when you start, the cur has to be not null, and the stack the stack has to be non-empty. So the cur is 1, which is the root. Cur is not null, first condition. Stack dot push cur. So what he'll do is, he'll take this one and he will push it. Okay, and it says cur dot left. So I'll go cur dot left. That's 2. Perfect. Again you come back, cur not null. So stack dot push cur, and cur will go again cur dot left. So cur will again go to 3. Again come back, stack dot push 3, cur equal to cur dot left. So this will become null. I hope you have understood. I went like left, 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 and why am I not printing? Because I print the extreme left, right. After that I print the right. This is a subtree for which I do not have a left. So left is not printed. So right will be printed, then 3 will be printed. So I have to go to the right. Perfect. So how will that happen? Cur is null. So the moment I come back again, I see cur is null. So this if is not executed. So this guy is executed. What happens is, temporary is st.top right, 3's right, 3's right is 4. So temporary is a variable that's assigned to 3's right, that's 4. So I assign that. Is temporary null? No. So cur will be reassigned to the right. So cur is reassigned to 4. Okay. Now again you come back. Stack will say, okay, I'll take you and I'll move left. So when 4 tries to move left, it again finds a null. So again this will happen. The moment you again come back, temporary this time says stack dot top 4. What's your right? Your right is 5. So temporary is assigned to 5. So what I see is temporary is not null. So cur is reassigned to 5. So cur will be reassigned to 5. Again I come back. Stack will say, okay, I'll store you. And 5, why don't you go to left? So the moment it tries to go to left, it will be a null. Again comes back. Temporary says stack dot top dot right. So temporary becomes 6. And this time temporary is not null. So the cur will reassign itself to temporary. So the cur becomes 6 again. Again it comes back, stack says, hey, why don't I take 6? And I'll say, cur, why don't you move left? So the moment it moves left, it becomes null. I hope you've understood. I went left, 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 right, there was no left, so again right, no left, so again right. Similar to post order. Now, the moment I've reached here, it's time to print this. How will you print this? The moment you come back again, cur is null. So temporary this time says stack.top right. So that's null. So temporary becomes null this time. The moment temporary becomes null, what happens? See, temporary says, okay, I'm going to pick up the topmost element and pop it out. So he's going to take up this element and pop it out. So I popped it out. At the same time, I'm saying post order, why don't you add it? So post order says, okay, I'm going to add this. So this is my first post order. Logically correct. Left, right. So on this is the extremist, right? So that's why. Next, what is this for loop for? What is this while loop for? It states if the stack is non-empty and the temporary is 6, if it is equivalent to stack.top right, so what is top? 5. So 5's right, it is. I have to go back. I have to go back to 5. And if I'm going, so 5's right, it is. I have to go back. I have to go back to 5. And if I'm going back to 5, I'll say temp, why don't you reassign yourself to 5, right? Basically the previous value, and pop yourself out. At the same time, the post order will also add it. So I've taken it. Perfect. Again the while loop executes, and again I check 4's right is 5 or not, and it is. So I again do the same thing. I again pop this value out and I reassign temp. At the same time I say post order, why don't you have yourself? Again I do the same thing. I say 3 is your right 4. Yes. So I take 3 out and I reassign temp. At the same time I say post order, why don't you have? So basically I'm going have root. I've gone. Now what's left? 2. 2 is your right 3? No. So there is no more root for 3. There's no more root for 3. So I'll not go back. Now when I don't go back, what happens? This while loop is over. This time cur is still null. So I'll go back again, and temporary will be st.top right. So when I have st.top, that's 2. Cur right will be null again. So if I have null again temporary, I again perform these following steps. Temporary says, why don't you take the top? So 2 is taken and it's popped out. And the moment I take 2, it says post order, why don't you have it? So post order has it. Does it have a root? Like, does it have a root? It says this while loop will say no, it doesn't have a root, so nothing to be printed. So it's over. Again I'll come back, and the cur is still null. So I'll say st.top.right. This time the top is 1. So the right becomes 7. So if I have null again, temp is over. Root temp 3 is your right 4. Yes. So I take 3 out and I reassign temp. At the same time I say post order, why don't you have? So basically I'm going have root. I've gone. Now what's left? 2. 2 is your right 3? No. So there is no more root for 3. There's no more root for 3. So I'll not go back. Now when I don't go back, what happens? This while loop is over. This time cur is still null. So I'll go back again, and temporary will be st.top right. So when I have st.top, that's 2. Cur right will be null again. So if I have null again temporary, I again perform these following steps. Temporary says, why don't you take the top? So 2 is taken and it's popped out. And the moment I take 2, it says post order, why don't you have it? So post order has it. Does it have a root? Like, does it have a root? It says this while loop will say no, it doesn't have a root, so nothing to be printed. So it's over. Again I'll come back, and the cur is still null. So I'll say st.top.right. This time the top is 1. So the right becomes 7. So this time temporary becomes 7. So the temporary is not null. Cur is reassigned to temporary. So cur becomes 7 this time. So the moment the cur becomes 7, again start your same thing. Stack.push 7. And cur becomes cur.left. The 7 will go to 8. Again comes back. Stack.push 8. Cur says, why don't you go left? The moment it goes left, it becomes null. Okay. So this is what is being stored in your stack as of now. And it's null. Again comes back, temporary says stack.top 8. What's your right? He says st executed for n times. And first you. So before starting the video, I would love to thank Reliable for sponsoring this entire tree series. So if you're before starting, right, null. So the moment you see that the intuition. So before in order, what is the post order before watching this video? So what I'll do is I'll create three different lists. The first one will be the pre-order list. Well, the next one will be the in-order list, and the next one will be the post-order list, where I can definitely store all the pre-orders, in-orders, and the post-orders. So let's start. So remember, whenever you start, you take the root of the node and you insert the number as 1. That is what you will always do when you start off with. I'm going to tell you some rules that you have to follow. Okay, so remember this. If whenever you're taking out an element from the stack, if that number is 1, then that guy will go on to the pre-order. Remember this, that guy will go on to the pre-order. Okay, and after that you will push that number by doing a plus plus. Okay, you'll push that number by doing a plus plus, and if there exists a left, you will enter that left. That is what you will do whenever you get a number equal to 1. What if you get a number equal to 2? A number equal to 2, whenever you get, what you will do is you will say that, okay, this is the second time. So as you know, second means, like in pre-order it's root, left, right. So that's first. In order it's left, root is in the second. So the number is 2. You'll say I'll take it to the in order. I will increment the value. Yes, I'll increment the value, and I will push if there exists a right. If there exists a right, because after left, root, there is right. What if it's a 3? Yes, what if it's a 3? If it's a 3, is the last time, right? So what you'll say is, okay, I'll take this into my post order. I'll take this into my post order, and there's no need to pop or do anything. Fine. So at every iteration, this is the initial configuration that you start off with. And at every iteration, just make sure you take out the topmost element of this, right? So what is the topmost element? That's 1. What is the value? What is the number? 1. So it'll go to the pre-order. So pre-order takes 1. And again, you will reinsert 1 comma. Like if I just rewrite it over here, I can just write 1 comma 2 is what is reinserted into the stack, and the pre-order will have 1. Okay, now does there exist a left of 1? Yes, there exists. So you'll insert 2 comma 1 into the stack. Perfect, done. Now on the next reiteration, you again take the topmost value. That's 2 comma 1. So the number is 1. Again, if the number is 1, you will take that into the pre-order. So once you've taken that into the pre-order, what's your job? Your job is to increment this And if there exists a left of 2, there does exist, you will take that and you will insert that into your stack. So what I'll do is I'll insert that into my stack. Right after this, on the next iteration, you again get 3, 1. So again, that will be 1. Hence, it is a pre-order. So I'll take that into the pre-order. You will increase it. And if there exists a left, there doesn't. So you will not insert anything. Now, the next iteration, when you come back, you get 3, 2. Now, when you get 3, 2, what will you do? It's a part of the in order, right? So it's a 2. 3, 2, 2. So it's a part of the in order. So 3 will go to the in order, right? And again, you'll increase it. So this will become 3. And does there exist a right? Does 3 have a right? No. So no more insertions. Again, you come back. This time you have a 3, 3. So it's 3. So it'll go to the post order, right? And once it goes to the post order, like this will no more be incremented. So this won't be in your stack any further. Then the next iteration, when you come across, you have a 2, 2. So can I say 2, 2 means number is 2? So it'll go to the in order. So you go to the in order, right? Then you will do a plus plus. Does it have a right? Does 2 have a right? Yes, that's a 4. So it'll say 4, 1. Why don't you go and insert yourself? Perfect. So I've inserted it, right? Again, you'll come across, it's a 1. Whenever it's a 1, it goes into the pre-order. So 4 will go into the pre-order. Perfect. After that, plus plus. After that, does 4 have a left? No, nothing done. Again comes back, 4 is having 2. So this time it will go to the in order. And this will be a plus plus. Does 4 have a right? No. So again it will come over. This time it's a post order. So 4 will go to the post order. And we will, like, this will no more be incremented. So it's over. On the next iteration, when you come back, you get 2, 3. Again, you got something which has a value 3. So that will be a part of your post order. And can you increment 3? No. So it's over, right? So the next iteration, you get 1, 2. Now, if it is a 2, it will go to the in order. So it goes to the in order. And this time you increase the value. And after that, you take the right. So what's the right? 5. So 5, 1 this time will take place. Yes, there will be a 5, 1 that will go in. Next, you again come across. It's a 5, 1. So this 5 will be the part of pre-order. And this will take a value 5, 2. And does 5 have a left? Yes. So 6, 1 will be inserted. Perfect. Again, you come across 6 is having 1. So 6 will go to the pre-order. Does 6 have a 6 will be incremented? Does it have a left? No. Again comes over 6, 2. It's a 2. So it will be a part of in order. So take it to the in order, increase it. Does 6 have a right? No. Again come over 6, 3. So 6 is again into the post order. So you just take it into the post order. So once you've taken that into the post order, what's your job? The job is very simple. You just take it off. Next again you come across 5, 2. So the 5 will go across to in order and the value will increase to 3 and you have a right. So that is 7. The 7, 1 will be inserted. Perfect. Next you again come over 7, 1. So that will go to the pre-order. So 7 goes to the pre-order. Value increased. Does it have a left? No. Comes over again 7, 2. Goes here. Value increase. Does it have a right? No. Again comes over 7, 3. Goes to the post order at a single right? Because it's a they want you to do that in like one piece of code. That is when these kind of problems can be asked. So guys, want you to do that in like one piece of code. That is when these kind of problems can be asked. So guys, as usual, the C++ code is on the left and the Java code is on the right. So we're given the root of the tree, right? So what we do is we start off by declaring a stack of pairs. That is what I'll do. Right after that, I just push on the root with the number as 1 initially. After that, I've defined a list of vector of pre, in, and post where I'll be storing all the traversals. I keep on traversing till the stack is not empty. I get the topmost element. Yes, I get the topmost element and I pop it out. After that, if the topmost element's second, or in Java it's the num, right? Because it's a self-created pair class. If that's 1, what I do is I just take it into my pre-order. If that's 2, I take it into my in order. If that's 3, I take it into my post order. If it's a 1, if you remember, it was a plus plus. So I do a plus plus, and then I again push it back to the stack. And if there exists a left, I'll also push that. Over here, the similarity, plus plus, and if there exists a right, I'll push it onto the stack. And over here in the post, I'll not do anything. I'll not push it back again, right? I'll erase it, so I'll not push it back again. So if I do this, I will end up generating all the traversals with a single piece of code. So I hope you've understood the entire explanation. I'm generating all the traversals with a single piece of code. got that right. Some rules that you have to follow. Took a lot of efforts to. After that, if the top, you can say to n. Why thrice for time complex space complexity? Code is on the left, and the Java code So before starting this video, I'd love to thank relevant to the left, right, then I have to go to the right. On the left, go to the right, so it's going to be 8, then a 7, then a 6, then a 3, then a 1. That is what the post-order traversal for this given binary tree will be. So what we will do is we will initially take 2 stacks. This is the first stack, stack 1 that I take. Then I'll be taking stack 2. Okay, so let's take stack 2. Now what you will do initially is you'll take the root of the tree and you'll enter that into the stack 1. That's the initial configuration. That is what your initial configuration will be when you start off with. Now let's get started. So when you start the program, you take the first guy out. And the moment you take this out, you put that into your stack. Okay. After that, if this guy has a left that it has, you'll take that. If this guy has a right, you'll take that. So you have taken the left as well as right. Now at the next step, at the next iteration, when you come across stack dot top, the top element is 3. So take this 3, put this into your stack. Okay. And again, same thing. Stacks left, that is 6. Stacks right, that is empty. So if it is empty, you don't need to put, but put the left. So I put it right. Now again, come back on the next iteration. Take whatever is at the top, put it onto your stack. Okay, so I put that into your other stack. Next, whatever you have taken, if there is a left of 6, it is empty. So if it is empty, you don't need to put, but put the left. So I put it right across stack dot top. The top element is 3. So take this 3, put this into your stack. Okay, and again, same thing. Stacks left, that is 6. Stacks right, that is empty. So if it is empty, you don't need to put, but put the left. So I put it right. Now again, come back on the next iteration. Take whatever is at the top, put it onto your stack. Okay, so I put that into your other stack. Next, whatever you have taken, if there is a left of 6, take it. If there is a right of 6, take it and put it into your stack. Perfect. Now what is in the next iteration? When you come across, you get 7. So you'll take 7, you'll put that into your stack 2. Once you put that into your stack 2, for 7, does there exist a left? No. Does there exist a right? Yes. Take it and put that into your stack. In the next iteration, when you come across, take this 8, put that into your stack 2. And again, does 8 have a left? No. Does 8 have a right? No. So you'll not do anything. In the next iteration, when you come back, you'll get a 2. So take this 2 and put that into your stack 2. Now what you'll do is, you'll again look, does the 2 have a left? Yes. Does the 2 start from the stack be up, so you'll get 6. Then 3 will be up, so you'll get 3. Then 1 will be up actually into the stack. So what I've done is, I've taken the topmost element and I've pushed it into the other stack. After that, if there exists a left, put it onto the stack 1. If there exists a right, put it onto your stack 1. Once your stack 1 becomes empty, just pop out every element from stack 2 and put it into your post order. Before starting this video, I'd love to thank relevant. So before starting this video, I'd love to thank Relevant for sponsoring this entire tree series. So for this binary tree, what's the maximum depth? 1, 2, 3, 4. So I can say the maximum depth or height of this binary tree is nothing but 4. So we got to figure that out. So in order to do that, what is the traversal that we can use? We can either use the recursive traversal, or else we can use the level order traversal, which doesn't require any recursion. Now, what's the disadvantage of using that? We have to use a queue data structure, which at the worst case might end up taking a space complexity of big O of n. The recursive doesn't uses any space complexity, but it does use the auxiliary space, right? And the auxiliary space can go up to as high as big O of height of the binary tree. Again, the recursive and the level order might end up taking like similar kind of space complexity if you consider the worst case. Like for this level order, the worst case will be when you're given a complete binary tree, right? When the last level is completely filled, then this level order will end up taking big O of like n near about space, because the last level is gonna have a lot of nodes. But if you talk about the recursive solution, then whenever you're given a skew tree, this is what you call a skew tree, a linear tree. Whenever you're given a linear tree, the recursive traversal will end up taking stack space as equal to the number of nodes. So both have their worst cases. You can use any of the traversal in order to compute the maximum depth. You can use the recursive, or you can use the level order traversals. Generally, people tend to use the recursive traversal because generally in binary tree, trees are not skew. Rather, trees end up having a very very small height of log n in almost all the cases. That is the reason we use recursive. But again, you can use any of them. As I said, both of them have their own worst cases. So if I think of a logical answer, can I say if I'm standing at any given node, and the answer will be 1 plus maximum height of this left side and the maximum height of the right side, like whichever is having the maximum height. Can I say 1 plus, because 1 for the current node, and the maximum on left or the maximum on the right can give me the answer. Like logically this should be the answer, isn't it? So why can't we use a recurrence and try to figure out, like, for the left tree, for the right tree every time? Let's see. So initially we start at the root of the tree. Now we do not know the left height, or neither do we know the right height. So what we will do is, at first we will move to the left and then we will move to the right. But at first we will move to the left. Okay. So when you move to the left, this guy doesn't have a left. So 1 plus max of left will be 0 for this guy, max. Because for this 2, if I write 1 plus max of left will be 0, comma, what's the right? Again 0. So can I say for this 2 guy, the height is indeed, like if you're standing over here, the height is indeed 1 plus max of 0 on left, 0 on right, that's 1. So can I say this guy got me a height of 1? Perfect. Now I came across with the height 1 from this side. Now I am on the right side. So I come across 3 and I know the answer will be 1 plus max of left and max of right. So we again go to the left and we again go to the right. Okay. Now when we come across over here, I know one thing. For 4, the answer will be 1 of max plus left, max plus right. So again we go to the left. So on left for 5, we know the answer will be 1 plus max of left, that's 0, comma right, that's 0. So we can say it's going to be 1 for this 5. Perfect. So whenever you're standing at 4, you actually said 1 plus max of left. What did left give you? 1. What will right give you? 0. So can I say for this 4, the answer came out to be 1 plus max of 1 comma 0. That's 1 plus 1, 2. So for this 4, I ended up getting a height of 2. Now, when I'll come to 6, for 6, the answer will be 1 plus max of, for 6, the left will be 0, the right will be 0. So can I say for 6, the answer will be 1? Perfect. Now, when I'm at 3, can I say for 3, the answer will be 1 plus max of, now the left has been computed, that's 2, and the right has been computed, that's 1. So can I say 1 plus max of this, that's 1 plus 2, 3. So can I say from the left I got a 3. From the right I got a 3. From the left I got a 1. So for this guy 1, can I say the answer will be 1 plus the left guy came out to be 1. The right guy came out to be 3. Hence the answer I have to find. And once I figured that out, what I'll do is 1 plus max of left height and right height. Simple as that. It's a simple. Hey everyone, welcome back to the channel. So before starting the 4. Order, the worst case will be when you recursive traversal, because plus maximum height of this left side through, and whenever the root is not Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving the problem check for balanced binary tree from the Freaka tree series. So what is a balanced binary tree? So in any given binary tree, there will be a lot of nodes. Okay. So for every node, the height of the left subtree and the height of the right subtree, their difference should be lesser than equal to 1. Like you cannot have a difference which is greater than 1. So for an example, if I consider this first binary tree, you can see for this node 3, the left height is 1 and the right height is 2. So there is a difference of 1. For this, there is no left subtree, there is no right subtree, right? So you can say that the height of left right is 0. For this, the left subtree is a height 1, the right subtree is a height 1. So the difference is again 0. For this guy, the left subtree is 0, the height of right subtree is 0. For this guy also, the left is 0, the right is 0. So I can say this is a balanced binary tree. But when I come to the second example, if I stand over here and I look at the right's height is 1, whereas the left height is 1, 2, 3. So I can say the left height is 3. So the difference between them is 1. For this, there is no left subtree, there is no right subtree, right? So you can say that the height of left right is 0. For this, the left subtree is a height 1, the right subtree is a height 1. So the difference is again 0. For this guy, the left subtree is 0, the height of right subtree is 0. For this guy also, the left is 0, the right is 0. So I can say this is a balanced binary tree. But when I come to the second example, if I stand over here and I look at the right's height is 1, whereas the left height is 1, 2, 3. So I can say the left height is 3. So the difference between them is 3 minus 1, 2. So I want lesser than equal to 1. Like I cannot have more than 1 as height. So I can say that this binary tree is no, and I just given binary tree, the naive solution is going to be very simple. I go to every node and I figure out the left height, the right height, and I compare the difference, and I just say if the difference is greater than 1, I'm going to return a false. So I just do traverse for every node. Difference is greater. You can check out the pseudo code over here. Like I take a node, like it's a pseudo code. So I go to the left height, I find the left height. Very simple. You keep on going left, you keep on going left. If there is no left, go right, go left. Like wherever you can go till the leaf node, just keep on going and figure out the left height, figure out the right height. Again, very simple. Go right. If there is no right, go left. If there is like again right, go to the leaf node, figure out the right height also. So once you figured out the right height, what you can do is if their absolute difference, yes, if their absolute difference is greater than 1, you're going to return false, saying that they're not balanced. This is not a balanced binary tree. Or else, if this condition is not happening, then you go to the next node, and then you go to the next, and then so on. So you go to the left, and then again to the right, and you again follow the same procedure of checking left, right. And if anyone from left, right, anyone gives you a false, if anyone gives you a false, you return a false. Like if any node in bottom anywhere gives says you that this is not a balanced binary tree, you directly return a false. And if no one, like on left, on right, no one gives you, you're going to return a true. Bottom anywhere gives a false. From left, right, anyone gives you a false. If anyone gives you a false, you return a false. Like if any node in bottom anywhere gives says you that this is not a balanced binary tree, you directly return a false. And if no one, like on left, on right, no one gives you, you're going to return a true. Again, you have to be very good at recursion in order to solve this problem. So what's the time complexity of this? The time complexity of this is very simple. I can say a big O of n for traversal, and in order to find the left height, or in order to find the right height, we're going to take a big O of n every time I reach every node, because I at the end will traverse this much. And if it's a skew tree, just in case if it's a skew tree, I'm going to end up taking a big O of n complexity, which is apparently a lot, right? So that's going to take a big O of n. So I can definitely not try this solution, because this is a big O of n square solution. Now the only problem, in order to convert this big O of n to a big O of n solution, is since we have to write a boolean function, like I want to write a boolean function which returns me a true if it's a balanced binary tree, and it returns me a false if it is not a balanced binary tree. So how do I get the left height and right height? Because that's tough. In order to get the left height and right height, I have to do something else. This, if I can reduce this time, because this is where I'm taking an extra big O of n. So if I can omit this time, I think I can convert my solution to a big O of n complexity. So let's discuss the big O of n complexity solution. So in order to in order to get the left height and right height, I have to do something else. This, if I can reduce this time, because this is where I'm taking an extra big O of n. So if I can omit this time, I think I can convert my solution to a big O of n complexity. So let's discuss the big O of n complexity solution. So in order to understand the big O of n solution, there is a prerequisite. You should be knowing how to find the height of a tree in big O of n time. And if you don't know that, I already have made a video on that. You can find the link in the description. Go and check that video out. How to find the height of a tree in big O of n. This is the code that I did use in order to find the height of the tree in big O of n. Very simple. What I do is I just do a simple recursive traversal where I say LH, RH, and I know for any node, like if I'm standing at this node, this might have a height, this might have a height, LH and RH. What is the height of the tree? So if this right subtree is longer, can I say for this node, the height will be RH plus the node itself. So maximum of left subtree, right subtree plus 1. So in order to understand in brief, please go and watch my find the height of the tree video. So you should definitely know find the height of a tree video. Now, since this does this in big O of n, this is the height of tree. But I want this function to return me either a true or either a false. Right? I want this to be returned. And how can I manage a function which returns the height as well as true and false? So what I'll do is I'll just act smart. Instead of returning true and false, what I will say is if my function, like my tree is balanced binary tree, I will return the height of the tree. Okay, I'm going to return the height of the tree. So if I take this tree, this function is going to return me the height of the tree. And if it is not a balanced one, then I will return a -1. So as of now, this functionality returns the height of any tree. So I will try to implicate a functionality such that it returns a -1 if it is not a balanced binary tree. So what I know is if the left height, that's nothing but the left height subtree. So if the absolute of left height and right height is greater than 1, I know one thing, this is not a balanced binary tree. So instead of returning any further height, instead of returning this, what I'll do is I will return a -1. So at any moment, I find a height difference of left subtree and right subtree to be greater than 1, I am going to return a -1. Okay. Now you might think that, okay, this is okay, but how will this work? Very simple. If you're calling the left height and this is giving you the height, if this LH at any time is -1, if this is -1, or this RH, like if you're calling the functions at any time you get a -1, you are definitely going to return a -1. So you can insert it over here. The whole tree. So we go, there's no left, null, no x. So initially we are over here. So if node is null, no it's not, so we'll go to the left. So we go to the left. So we come to the 2. Again, we go to the left. We come here. Again, we go to the left. We come here. So when we reach 9, there's no left, there's no right. So the left height and right height is not there. Basically, when you call them, you will get the left height as 0. You'll get the right height as 0. So these two lines will not function. So max of left height, that says 0, 0. These two lines will not function. So max of left height, that says 0, 0 plus 1. So this is going to return you a 1. So from this side, like when 3 called its left, it got as 1. Now 3, it's time for 3 to call its right. So when 3 call its right, it'll go to the right and it'll execute node is null and it'll return a 0. So it got a value 0. So 3 from the left got a 1, from the right got a 0. Again, the height difference is not that much. So you have a 1, you have a 0, which is permitted. The difference is 1. So you got a 1, you got a 0. Again, maximum of 1, 0, that's 1 plus 1, 2. So this guy returned a height of 2. Again, makes sense because the height of the tree is 2 if you stand at 3. Now you add 2. The 2 guy went to the left and got a height of 2. Now when it goes to the right, it gets a height of 0. So this is the moment. When you add 2, you went to the left and you came up. Like when you add 2, the left height came out to be 2. And the moment you went to the right, since 2 did not have a right, you got a height as 0. So what happened was 2 and 0 have an absolute difference of greater than 1. So what this guy returned was -1. So the moment 1 saw that a -1 is returned, it directly returned a -1. So if you're getting a -1, there's no need to visit the other part of the tree. And you can say that if you have got a -1, the tree is indeed unbalanced binary tree. So the C++ code is on the left and the Java code is on the right. Very simple. I call the DFS, like I call the function, and if it doesn't returns -1, then it's a balanced binary tree. If it returns the -1, it's not a balanced binary tree. Simple as that. Root is null. Left height, if by chance left height is -1, return a -1. Right height, if by chance the right height is -1, return -1, else absolute is greater than 1, return -1, or solution is going to be very